Let us now consider the addition law. It provides us a way to compute the probability of event A or B or both A and B occurring. And this is how the law is written. The probability of A union B is equal to the probability of A plus the probability of B minus the probability of A intersection B. Remember, union, it's OR. So you can think of this as the probability of A or B will be equal to the probability of A happening plus the probability of B happening. But we have to subtract the probability of both of them happening at the same time, because otherwise we would be double counting. Here is again an example from Bradley Investments. Two events. Markley is profitable and Collins is profitable. Remember, for union it's OR. So Markley profitable or Collins profitable. We know that the probability Markley is profitable is 70%. We know that the probability that Collins is profitable is 48%. And we also calculated from an earlier slide that the probability that Markley and Collins is profitable is 36%. Let's therefore use the addition law. Why don't you write down your answer first before I show the answer? Remember, this is the addition law. Plugging in the numbers, %, which is exactly the same as that we obtained earlier when we were computing the probability of the union of M and C. Now we come to the notion of mutually exclusive events. Two events are mutually exclusive if the events have no sample points in common. They're mutually exclusive if when one event occurs, the other cannot also occur. There. These are two mutually exclusive events because the two circles have no intersection. If a sample point is in A, it cannot be in B, and vice versa. And which therefore leads to this mathematical result. If two events are mutually exclusive, then the probability that of their intersecting will be equal to 0. Here is the addition law. Precisely because the probability of their intersection is 0, if we plug 0 into the addition law, then we will get the result that the probability of A union B will just be equal to the probability of A plus the probability of B. Finally, the notion of conditional probability. It is the probability of an event given that another event has occurred. So this is how we denote it. The probability of A given B is written this way. And this is how we compute the conditional probability. The probability of A given B is equal to the probability of A intersection B divided by the probability of B. Can you figure out how to compute the conditional probability of B given A? Look at Bradley again. What is the probability that Collins will be profitable given that Markley is profitable? We know that the probability that Markley and Collins are both profitable equals 36%. We know that the probability that Markley is profitable is 70%. Plug those numbers into the law for conditional probability and we get, which is 51.43%. Can you compute the probability that Markley is profitable given that Collins is profitable? The multiplication law, finally, is a way to compute the probability of the intersection of two events. Remember, we could have computed this directly from the example shown earlier, but this is another way. And this is how the law is written. The probability of A intersection B equals the probability of B times the probability of A given B. As you will see, it's just a mathematical rearrangement of the previous equation for conditional probability. And using the example from Bradley Investments, what is the probability that Markley and Collins will be profitable, i.e. the probability of M intersection C? We know these probabilities, probability of M and the probability of C given M, from 2 slides earlier. Plugging them into the equation, we will get 36%, which is exactly the same as the probability of the intersection that we computed much earlier. One can also compute the joint probability table. Please take a few minutes to consider for yourself how this table was constructed. As you will see, the column on the right hand side will add up to 1, and the row at the bottom will also add up to 1. What are independent events? If the probability of event A is not changed by the existence of event B, we say that the two events are independent. Here is the mathematical formulation of two independent events. A and B are independent if the probability of A given B is equal to just the probability of A itself. Alternatively, the probability of B given A is just the same as the probability of B. And here is the multiplication law for independent events, which can also be used as a test to see if two events are independent. The probability of A and B intersecting will just be equal to the probability of A times the probability of B. And here is another example. Are the events M and C independent? Let's check. We had earlier calculated the probability of M intersection C, and we also know the probability of M and the probability of C. Does this equality hold? Let's plug in the numbers that we already know. As we see, no, the equality does not hold. Hence, we conclude that the two events are not independent. Be careful. Do not confuse the notion of mutually exclusive events with that of independent events. Two events with non-zero probabilities cannot be both mutually exclusive and independent. Can you see why? And here is the explanation. If one mutually exclusive event is known to occur, then the other cannot occur. But if the other cannot occur, that means that the probability of the first affects the probability of the second, i.e., when one occurs and the other does not, that means that the probability of the second event is reduced to 0, i.e., they are dependent. Conversely, therefore, two events that are not mutually exclusive might or might not be independent. I will suggest some exercises at the end of the book to try.